So this is Llama 3.1 8 billion parameter model. And this is Llama 3.1 70 billion parameter model. And here we're trying to solve difficult math problems. And here is the Llama 3.2 1 billion parameter model on this blue curve. And here is Llama 3.2 3 billion parameter model. Here's the curve for it. And here we can see the 1 billion parameter model is outperforming the 8 billion parameter model, and the 3 billion parameter model outperforming the 70 billion parameter model. And this is on the Math 500 benchmark accuracy. So how is that even possible? A model that is more than 20 times smaller can outperform a model that is as big as 70 billion parameter model. So this is possible through test time compute. So there is the train time compute when the models are being trained, but here through test time compute, the model parameters do not change. There's no training that happening here. It's just an algorithm of how we produce an answer, how we make the model reason to produce the better answer eventually. So the idea here in test time compute is that we encourage the agent to reason more at inference time in order to produce a higher quality answer. So there are multiple strategies to do this. We call them search strategies. So the first and simplest search strategy is best of n. In best of n, we have a math problem. We make the LLM, or we make the agent, produce candidate answers. So we sample multiple answers, not only one answer. Out of these n submitted answers, we have a verifier that's going to select the top or the best answer. A more advanced version of this is the beam search. One problem with the best of n is that it looks only at the final answer. It doesn't measure or assess the quality of intermediate steps or the reasoning that led to the final answer. In the beam search, here we try to see whether the reasoning and the steps taking the path towards the answer is actually correct. So here we have n beams. Every beam is going to have a width of m, and every beam is going to produce multiple solutions. At every step, we select the top n over m steps. So in this case, n is 4 and m is 2, so we select the top 2 solutions to move further. And then at the end, we select only the final answer, like one answer. So this allows us to explore a little bit more, to have multiple solutions and multiple branches in the tree, and then we keep pruning until we get a better solution. So this wins over the simple one, because here we don't look at the intermediate steps at all. But in the beam search, we actually also assess the reasoning behind the solution, and we try to take the best reasoning overall in order to converge eventually to the best solution. Now, the third method, or the third search strategy, takes this even further. So instead of having just one tree, we have now multiple trees, diversifying the solutions that are attempted, the reasoning paths that are taken in order to solve a problem. So these are the 3 search strategies. Let's see how they are implemented. So for the implementation, first we have the math problem that we're trying to attempt. Then we have the LLM. The LLM will try to generate the sample answers, right? Like it will try to generate multiple intermediate steps. Those steps will be scored by what we call the process reward model. The process reward model is a small LLM that is trained to verify the results of intermediate steps of LLMs. It will select or score the candidates, and then based on the search strategy, the top candidates or top solutions will be selected to move further in the reasoning chain. And then we keep generating and moving through this loop until we eventually reach a final answer that has the most likelihood to be the right answer. So if we go back to the first diagram, we see that the more we increase the number of reasoning steps, or the number of iterations in the loop, the better the final answer, or the better the accuracy is. So here, as you can see, we have 256 steps. A 3 billion parameter model could outperform a 70 billion parameter model, while for small number of steps, like 4 generations, it's worse than the 70 billion parameter model. So this is the baseline. And this is after the 256 generation steps. Okay, so now let's recap. We have a small model. We do sampling. So we make this model produce multiple answers, and then we have a verifier that verifies the answers to have a chain of thoughts and to have multiple reasoning steps to then select the best solution and reasoning path in order to get the final answer, the best possible final answer eventually. So small model plus sampling plus a verifier, we have seen that the results are equal or even a little bit better than a bigger model. So this is the same trick that Frontier Labs have used, like O1 and DeepSeek R1, the idea of scaling test time compute. Okay, so now this method has limitations as well, right? So first you need a good verifier, and it's hard to tell what a good verifier looks like. So it needs to be an LLM trained to select the best possible answer. So this is also like a difficult task on its own. You might need to test multiple verifiers and see how it performs. So the second thing is that it works when there is a right answer. So this method only works if there is a right final answer at the end that we can measure, like math, coding problems, and reasoning problems. So if there is no right answer, then the verifier will not have no idea or no criteria on how to select the best answer. And then the third thing is that we trade latency and tokens for quality. As we have seen, zero shot from the 70 billion parameter model to get a similar performance or to outperform it. We needed to perform 256 steps of generation. We'll have bigger latency, and we're going to use a larger number of tokens overall. So yeah, that was all. So this technique could be used if you have difficult tasks and you want to increase the model quality without using a bigger model. And yeah, I hope you learned from this video. If you want to learn more about how AI agents work in detail, not only as black boxes, make sure to subscribe. And thank you so much for your time. See you in the next one. Bye bye.